Hi, my name is Sagnik, and this is the third part of the tutorial on optimal power flow. So in this last section, we see an extension of optimal power flow, which we call the security constraint optimal power flow. We'll further see the challenges of SCOPF, and we'll figure out some of the applications of OPF and SCOPF in power systems. As we all know, in a day-to-day operation, the power system faces several contingencies. Such failures or contingencies can include line outages, generator outages, or maybe a blown up transformer. Now, under all such failures, it is assumed that the system still should operate reliably. We call this criteria N-1 criteria. It means that under a possible failure of one element, which is N-1, the system is still reliable. We can further extend this criteria to N-1, which means we have another element failure, subsequent outages, or we can also have N-2, which means we have two equipment outages at the same time. In general, we consider N-K outages, but it's very rare because we have a lot of different combinations of K different items. So as of now, we'll be focusing on N-1 criteria for security constraint optimal power flow. So as we discussed before, SCOPF is nothing but a combination of OPF and a sense of security, which in this case we are considering as a N-1 secure system. The basic point that we are trying to address is that how do we minimize the cost of operation while ensuring that operating constraints are satisfied in both the normal and the contingency states. Basically, part B is the addition to the OPF. So it is required that our system has satisfied all the operating constraints and still minimizes the cost of operation even when there is a N-1 contingencies. In this case, we are only assuming that either branch or generators have been outaged. In the next slide, we will see how we can formulate the optimization problem for SCOP. The main objective function remains the same. In this case, we are trying to minimize the operating cost. Again, as a basic assumption, this operating cost includes the cost of fuel. As we have already seen before, GK includes the power balance constants, and HK less than 0, this includes all the limits and capacity constants. These limits and capacity constraints are for lines and generators. So we now add another constraint which takes into account the security. We will be focusing our discussion on this constraint as of now. Here, there is another thing to note is that K equals 0 represents normal conditions and K equals 1 to N represents contingency condition. So for the last constraint, we have U of K minus U of 0 less than some tolerance. So let's say, for example, we have some power flow in our normal case, and we have a power flow under N-1 contingency case, which is K. So this power flow is U, and once a line is outage or a generator is outage, it might happen that subsequent line power flows might increase. So let's say the new line power flow is given as Q of T. To ensure that any failure of a single component do not violate any limits, we have to minimize the difference between the new line power flows and the original power flow, which is given by this expression. So this tolerance actually is a vector of maximum allowed adjustments after contingency K has occurred. So if you add this additional constraint, our generator will be dispatched in such a way that under one single failure, none of the lines will be overloaded. So the security constraint optimal power flow has certain challenges. When you have a large network, we have thousands of lines, hundreds of controls. So in this case, we have to consider a large number of constraints and large number of scenarios. In most of the cases, the security constraint OPF is nonlinear and non-convex, which makes it extremely difficult to solve. Additionally, we also have to consider certain discrete binary variables, such as the position of transformers, phase shifting taps, or the status of capacitors and reactors. So the discrete variables, the non-linearity of the program, and the non-convexity of the problem introduces a lot of challenges while solving SCOP. So with this, we sum up the basics of optimal power flow and its extension of security constraint OPF. The last slide actually gives us some of the applications of OPF in power systems. So first, we use OPF in constrained economic dispatch. We also use OPF in contingency response. So once when failures have happened, we now want to operate the system reliably. In cases where there is voltage instability, OPF can also play a part to figure out what are the good solutions. Apart from that, other applications include seasonal adjustment, reactive power planning, volt bar tuning, facts devices, different scenarios when you use facts, and what impact it has on the power system, as well as different base case development of the system. For more information on the application, I suggest the students should look into this paper by Dr. Mountford, which talks about the practical applications of optimal power flow. Here are some of the references. You can always go to Power World, and they have the security constraint OPF, and they also have market modeling for OPF, and you can also download Match Power, as you have seen before, to play with the optimal power flow solution.